Hi everyone. So in this video, we're going to be talking about the relationship between the graph of a function and its inverse function. So I want to jump right into an example that we'll use to kind of illustrate what this relationship is. So we're going to start with the example of the original function being x cubed and then its inverse being the cube root of x. So I want to fill out tables for each of these functions and then sketch their graphs so that we can see what does it look like the relationship is between those two graphs. So I'm going to start by filling out this table for x cubed. So as we cube -2, we get -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. And then to fill out the table for the inverse function, you could just take the cube root of these various numbers, but you could also remember how, what the relationship is between a function and its inverse. So when you have an inverse of a function, the roles of inputs and outputs are going to switch, right? So instead of having these numbers as your inputs, those are going to be your outputs and these are going to be your inputs, right? So I'm going to make my input column have -8, -1, 0, 1, and 8. And so that is going to give me outputs of -1, 0, 1, and 2. So again, basically the x values and the output values have switched places on these two tables. And one thing I just want to mention is that, the function x cubed and the cube root of x, in some ways it's kind of a funny function because there are these three places where the inputs and outputs are actually equal. And so that's going to be the same for both of them, right? Input and output are the same number. So we'll see that actually will help us visualize the relationship between these functions a little bit. But when you're thinking about, what's the relationship between these two functions and their graphs, it might be most useful to focus in on these 4 points. Okay, so I'm going to go ahead and start sketching the graph of x cubed. So we have -2, -8. We have -1, -1, we have 0, 0, we have 1, 1, and we have 2, 8. And so I'm going to connect these, and then remember that the graph of x cubed, it doesn't go, it kind of, if you just were looking at this, you might guess that it goes like diagonally, like a straight line through 0, 0, but it doesn't. It does that kind of shape where it flattens out a little bit. For some reason, I always struggle with this last piece. Okay, there we go. Okay, so that's the graph of our original function f of x. So now let's go ahead and graph cube root of x. So it also contains these 3 points, right? We saw that it contains the point -1, -1, 0, 0, and 1, 1. But additionally, it contains the points -8, -2, and then 8, 2. And so I'm going to go ahead and connect these. And it has basically the same kind of shape as the cubed graph it does, in that it kind of flattens out when it gets close to 0, 0. Okay, so as you can see, these two graphs, they have the same shape, right? They're really like the same shape, just kind of positioned differently. And so there's a few different ways that we can think about the relationship between these two graphs. The first one that I want to point out is that the x and the y coordinates of these points have switched with each other, right? And so if we look at this, this point here, where the coordinates were -2, -8, well, the graph of the inverse function contains the point -8, -2. And then, whereas the original function contains the point 2, 8, the inverse function contains the point 8, 2. So that shouldn't be too surprising, right? Because that basically just goes hand in hand with what we've seen about inputs and outputs with functions and their inverses. So that's the first fact that you should know about a function, the graph of a function and its inverse function, is that all of the x and y coordinates are swapped with each other. And now notice that these two graphs actually overlap at these 3 points. And the reason that happens is because those are the points where the x and y coordinate are already equal, right? So if you switch them, you're going to get the same exact point that you started with. Whereas these 2 points, when you switch the x and y coordinate, you get a new point. Now, the other way that we can think about what's going on between these two graphs is that if I go and draw this diagonal line, so I'm going to draw a diagonal line that goes straight through the origin with a slope of 1. So what would be the equation for a line that goes straight through the origin with a slope of 1? That is the line y is equal to x. And so what's going on here is that if you take either the graph of f of x or the graph of f inverse of x, and you reflect it over the line y is equal to x, you're going to get the other graph, right? So if I take the graph of f of x and I reflect it over the line y is equal to x, I'm going to get the graph of f inverse of x, and vice versa. I personally think that fact, it's a good one to know, and it helps you kind of visualize what's going on. It's a little harder to do in practice. So when we get into an example where we have to actually sketch the graph of the inverse function of a graph, I think being aware of the fact that you're switching x and y coordinates will make it a little easier, but you also do want to know this fact. It's just kind of an important fact to know. So let me kind of summarize what we just saw here. So what we saw here is actually true in general. I don't know where this came from. It looks like a little smiley face, but I'll just ignore it. I'm talking about this thing. I didn't type that. Okay, so in general, the points on the graph of f inverse of x will have x and y coordinates swapped compared to points on the graph of f of x. And then the other way of thinking about this, like I said, which is really, it's equivalent, even though it might not seem obvious that it is, but equivalently, the graph of f inverse of x can be obtained by reflecting the graph of f of x over the line y is equal to x. So I want to look at a couple more examples of graphing a function and its inverse, and then kind of seeing this relationship for ourselves. And then we'll do an example where we don't actually have a formula for the function, where we just have to sketch the graph of its inverse based on the graph of the original function. So first example I want to look at is from, actually both of these are going to be from the last video. So the original function, and actually maybe let me color code this. So the first function will be x minus 1 squared, x is greater than or equal to 1. And then what we saw in the previous video is that the inverse function for this comes out to be the square root of x plus 1. So I just want to graph these two functions and see how they have that same relationship that we saw in the other graphs. Okay, so what does x squared minus 1, or x minus 1 squared look like? Well, that's a parabola that's been shifted to the right by 1. So I'm going to start by sketching it without the domain restriction, and then I'm going to erase the domain restriction just because, I don't know, I think that's easier to see. Sorry, I'm having trouble getting this right. There we go. Okay, so it's something like this. However, we only want the right side of this parabola. And so I'm just going to go in and erase the part that is the left side, right? So I'm going to erase this part away. It's kind of like a piecewise function, right? Where you're just erasing away the part that isn't what you're looking at. So that is our function f of x. And so what would the graph of square root of x plus 1 look like? Well, we know what the square root graph looks like, right? That general shape. And what does this plus 1 do? And maybe I'll even write these down. So this is a shift to the right by 1. And then this plus 1 is a shift up by 1. And so we just think about the square root graph shape and we shift that up by 1. And so that's going to look like this. And so what we can see is that these two graphs look like inverses, right? So I'm going to go in and draw this line y is equal to x. So we can see that they look like if you were to flip one of them over this dotted line, you would get the other graph. And we can also see things like the original function x minus 1 squared, that contains the point 1, 0, whereas the inverse function contains the point 0, 1. And you could test out other points on the graph and you'd see the same thing happening. Let's look at another one. So this one, we're going to look at f of x is equal to 2x minus 3. And so the inverse of that one came out to be 1/2 x plus 3/2. So remember, we had it written a little differently at first, but then we rewrote it like this in order to be able to graph it. So 2x minus 3, that's a line with a slope of 2 and a y-intercept of 3. So I'm going to go ahead and sketch that. So there is our first part. So our first function. So this is f of x. And then this other one is going to have a slope of 1/2 and a y-intercept of 3/2. So that's 1.5. So this one's going to be, I think, a little bit harder to sketch, but I will do my best. Oops. Something like that. I'll just stop there. So again, we can see that these functions are symmetric over the line y is equal to x. If you were to flip one of them over the line y equals x, you would get the other one. The other thing I want to point out that I think is kind of interesting, and this is always going to be true for linear functions. So notice the slope of one of them is 2 and the slope of the other one is 1/2. So in general, it's always going to be true that linear functions, if you have the inverse function, they're always going to have reciprocal slopes. And so the reason for that is basically just that, remember that that slope is like rise over run or change in y over change in x. And so with inverse functions, because the x and the y coordinates are switching, well, if you have, change in y over change in x and you switch the x and y coordinates, that's going to give you the reciprocal result. And so it's always going to be true that whatever your original linear function is, the inverse function will have the reciprocal slope. Okay, so now let's do an example where we're given a function f of x, but we don't have a formula for it. And what we want to do here is we want to sketch the graph of the inverse function. And so if all we have to work with is a graph, basically what we need to do is go in and switch all of the x and y coordinates. So I'm going to pick out a few kind of key points here. And these are going to be basically all the points that look like they have, nice whole numbers as their coordinates. And then we will use those points to come up with the points on the inverse function graph. So we can see that the original function contains the points -1, 6. You could also make a table. That might be a nicer way to organize this actually. 0, 4, 1, 2, 2, 1, and then we have 5, 0. And finally, we have 6, -3. And so what that tells us is that the inverse function is going to contain points where we flip these x and y coordinates. So it'll contain the point 6, -1, 4, 0, 2, 1, 1, 2. So we can already see that just like with the cube and cube root graph, there's going to be a couple of points that are on both of them. It's going to contain the point 0, 5, and it's going to contain the point -3, 6. And so now we can actually go and plot these points, and that will give us our graph. So the first point we're going to plot is 6, -1. So this is a point on the inverse function. Then we have 4, 0. So that's this point. We have 2, 1. So as we said, that's going to overlap with the original function. We're going to have 1, 2. Again, that overlaps with the original function. Then we have 0, 5. So that's here. And then finally we have -3, 6. And so the only other thing we have to be careful of when we go and connect these dots is to try to remember like what part of the graph is what. So most portions of the graph are kind of straight lines, but there is one curved portion of the graph. So maybe let's highlight which original points came from that curved part of the graph, and then we can make sure that on the inverse, we're making that part of the graph curved as well. So on the original function, the curved portion of the graph happened between 1, 2 and 5, 0. So this was the part of the graph that was curved. And so what that tells us is that this portion of the graph that comes from the same 3 points should also be a curved part of the graph, whereas the other parts will have straight lines between them. So starting with 6, -1 and 4, 0, those points are connected with a straight line. And so are these 2 points, but then this next portion of the graph should be curved. So it's going to be, more like that. I didn't do the best job of that, but basically it should have the same kind of shape that the original function did. So there is our inverse function. And so again, this one, I think it's a little harder to visualize. And this is kind of one of the drawbacks of just thinking about the line y = x, is that personally, I have a harder time with this one, visualizing this as a reflection over y = x, but it does work. If you were to kind of envision taking that purple graph and flipping it over this line y = x, you would get this green graph. But I think this method with the points is a more kind of explicit way to do it, where you can be sure that you're getting it right. Okay, last thing I want to talk about in this video is this issue that came up, or that frequently comes up when I'm teaching this class, about when we do this domain restriction, when we're making a function 1-to-1, why don't we do like the other half of the parabola? So I'm going to write out this question, what happens if we choose the left side of a parabola as our domain restriction? And so I want to do an example that basically is the same example we did earlier, but now choosing the other side. So let's say, and actually let me use a different color here. So let's say that our function now is going to be x minus 1 squared. But instead of taking the restriction where x is greater than or equal to 0 or 1, we're going to do x is less than or equal to 1. So I'm going to start by sketching that. So again, it's a parabola, but we're going to take part of it away. So this is the whole parabola. Now, in the earlier example we kept the right side, but for this example, I'm going to take only the left side. So I'm going to erase this right-hand side. And so that would be the function f of x. So remember, I'm going to go back to the example we did earlier. So here was the right side of the parabola. And so the inverse function ended up being the square root of x plus 1. And so notice that the square root of x, you might remember that the graph of the square root of x, it looks like half of a sideways parabola. And specifically, it's the top half of a sideways parabola, right? So when you have a graph that's a transformation of the square root of x, well, it's going to be like the top half of a sideways parabola shifted however much. And so what do you think is going to be the difference? Like what should the inverse be if now we're doing the left side of a parabola? Well, the inverse should be now the lower half of a sideways parabola. So how do we do that? Well, instead of saying positive square root of x plus 1, we just say negative square root of x plus 1. So what is that going to look like? Well, in terms of transformations, we have a reflection over the x-axis. So it's going to be the lower half of a sideways parabola, and then it's shifted up by 1. So it's going to look like this. Let's see, I'm trying to do my best on sketching this. Right, so this is just visualize, like maybe I'll even draw in the other half. So here was when we had the positive half. This is the right side of the parabola. And in that case, the inverse was this, right? It was this like square root graph that looked like that. Whereas now if we take the left side of the original parabola, then the inverse function would have to be the lower half of the sideways parabola. So how do you get that lower half? You just basically put a negative sign in front of the square root. So I just wanted to bring that up because I think it's a question that typically does come up in the class. As I mentioned before, the standard domain restriction that people will usually use for parabola is the right side, just because the natural way of drawing a square root graph is to do the positive half. So if you do want to do the left side of a parabola, you do have to remember this extra step of flipping the square root graph over the x-axis in order to get that bottom half. All right, that is it for this video. So in our next video, we will start to talk about quadratic functions, and basically we'll just be doing review of some stuff that you should have learned in your previous classes. And yeah, I'll see you all in our next video.